Okay, let's dive into this. Have you ever really, truly thought about what's happening when something falls? I mean, yeah, gravity pulls it down. We all get that. But it's so much more than that. It's this incredible story about energy, and we're going to follow it from start to finish.
So let's set the scene. Our hero for this story is a skydiver. They're way up there, thousands of feet in the air, basically still. Then they jump, and they start plummeting, gaining this incredible speed. On the surface, it seems pretty simple, right? But what's really going on here is governed by one of the most fundamental rules of the entire universe.
And this is it. This is the big one, the law of conservation of energy. You can think of it like the universe's #1 rule. You can't make energy from nothing, and you can't just make it disappear. Every single bit of it has to be accounted for. So let's be the accountants and follow the energy on our skydiver's crazy journey down.
All right, first things first. Before our skydiver even takes that leap, they're already loaded with energy, and it's all because of where they are.
This type of energy is called gravitational potential energy, or GPE for short. Think of it like this. The airplane had to burn fuel and do a ton of work to fight against gravity and lift that skydiver way up into the sky. All of that energy is now stored in the skydiver, kind of like a wound-up spring, just waiting to be let go. And you know, what's really cool is that this isn't some vague idea. Physicists can calculate it down to the decimal. The formula is actually pretty straightforward. You just take the mass of the object, multiply it by the force of gravity, which is pretty much constant here on Earth, and then multiply it by how high up it is. Simple, right? The higher you go, the more energy you've got banked. To make this feel a little more real, let's ditch the skydiver for a second and think about a cat. Say you have a 3.5 kilogram cat and it climbs up a 5.6 meter tree. Well, if you punch those numbers into the formula, you find out that cat has gained exactly 196 joules of gravitational potential energy. It's a real, tangible amount of stored energy.
Okay, so back to our skydiver. They've jumped, the story moves on. Now, they're not just high up anymore. They are moving fast.
And that energy of motion has its own name too, kinetic energy. If potential energy is all about where something is, kinetic energy is all about what it's doing. Any object that's moving, a baseball, a car, a planet, has kinetic energy.
And of course, there's a formula for this one too. It's 1/2 times the mass times the velocity squared. Now pay attention to that squared part. That's the secret sauce. It means that if you double your speed, you don't just get double the energy, you get 4 times the energy. That's why speed is such a huge factor in this equation.
Let me give you another example. Picture a 90-kilogram dancer moving across a stage at 6 meters per second. When you run those numbers through the formula, you find out they're packing 1,620 joules of kinetic energy. That's a ton of energy, and it's all coming just from their movement.
So we've got our two main players on the board, potential energy from being up high and kinetic energy from moving fast. Now let's see how they work together. This is where the story really gets good.
So let's go back to our skydiver, hurtling towards the Earth. Their height is dropping like a rock, which means their potential energy is going down. But at the exact same time, their speed is ramping up, which means their kinetic energy is going up. You see the connection here? It's a trade-off, isn't it?
You can literally picture it like 2 bank accounts. The GPE account, that big pile of energy they had at the top, is being spent. As their altitude drops, that energy has to go somewhere.
And this brilliantly illustrates exactly where it's going. It's not vanishing into thin air, it's being transferred joule for joule directly into the kinetic energy account. As one account empties, the other one fills up. It's a beautiful, perfect energy transfer.
And listen, this isn't some weird, isolated thing that only happens to skydivers. It is happening literally everywhere all the time. Think about a pirate ship ride at an amusement park. As it swings up, its kinetic energy turns into potential energy. As it swings down, that potential energy turns right back into kinetic. Or when a car hits the brakes, its kinetic energy of motion is transferred into heat or thermal energy in the brake pads. It's the constant busyness of the universe.
But hold on a second, it's not quite that simple. You knew there had to be a catch, right? In the real world, things don't add up so perfectly. There's a plot twist in our energy story. Because if you were to actually calculate the skydiver's fall, measure the potential energy they lost and the kinetic energy they gained, you'd find that something is missing. There's a gap. The numbers don't quite line up. And the reason is, our skydiver isn't falling in a perfect vacuum. They are crashing through billions and billions of air particles.
So what about the energy it takes to shove all that air out of the way? Well, this brings us to our final, crucial concept, dissipated energy. Sometimes people call it wasted energy, but that's not quite right. It's not destroyed. It just spreads out into the environment, usually as heat, in a way that's not very useful anymore. It's not helping the skydiver fall faster, let's put it that way.
And here it is. This is the solution to our mystery. That missing energy is the work the skydiver does against air resistance. All that friction transfers energy to the air particles themselves, making them jiggle around a little faster. In other words, it heats up the air. It's a tiny, tiny temperature increase for each particle, but when you're hitting countless of them, it really adds up.
So, and this is the crucial point, the law still holds. The books are always balanced. The initial gravitational potential energy doesn't just turn into kinetic energy. It becomes the final kinetic energy plus all that energy that got dissipated as heat into the air. Every single joule is accounted for. The law is never, ever broken.
And that brings us right back here, to you, probably watching this on your phone or computer. This little device in your hand is an absolute masterclass in energy transfers. You've got chemical energy in the battery, becoming electrical energy. That becomes the light from the screen, the sound from the speakers. And yeah, that warmth you feel in your hand, that's dissipated heat energy. It's all around us. So the question is, just looking around you right now, how many of these energy transfers can you spot?